Hello everyone. In this video, I will continue discussion on physical properties. And in the previous video, I discussed in very detail about the 2D and 3D material for ABCs, absorbing boundary conditions. And now I have SDR software, um, ASD Concrete 3D material, and damaged TC 3D. So um, this ASD Concrete 3D material uh, consist a lot of uh, precautions and parameters that needed to be carefully discussed and input in the STKO or OpenSees, and it requires some preset definitions, which I will explain in detail, and some sort of types of the loading nature for testing in all these parameters. So let's begin by renaming it. So it's based on the type. I will just rename it with Concrete 3D, right? Which means that you cannot assign this to a 2D material problem. Um, this is the density of the concrete here, and it involves this involve Druger-Prager plasticity model and failure envelope with the consideration of uh, confining effect as well here. So without wasting any further time, you can go to the OpenSeas documentation to study about it further, right? And you can find more details about this using the um, OpenSeas software here. So let's go to this properly where before discussing it here. So let's say I have this material definition for the SD concrete 3D material. So I will name it with the concrete 3D, and for this I need to choose a model that is no, I'm sorry, not in the definition but in physical properties. Concrete 3D, which is obvious that we cannot assign this to a 2D formulation problem, right? So this is the material, and let's look into the parameters. But before that, look at the behavior, that how uh, it's behaving if we model it. So it is a suitable material for masonry-like structures and infill walls and shear walls, and we can use it in those kind of formulations in the analysis. So the thing is, if you are trying to model it in this manner, then the best way to consider is to make sure that the formulation that you are using, you should be careful about the correct parameters definitions here. All the details are given in this OpenSeas documentation that are linked through STKO here. And the theoretical background is given here. I'm not going to discuss these equations because these are the engineering mechanics formulations, and behind there is a theory that's beyond the scope of this video series. Anyways, for further detailed explanation, it can be used and assessed here. They have a very beautiful sort of um formulation for the ratio of uniaxial to biaxial to biaxial stress for the concrete, and the confining envelope is given here, as well as the concrete uniaxial tension and uniaxial, cyclic tension, cyclic uniaxial tension, and cyclic uniaxial compression. It is given here, and it's a very beautiful simulation here. So just in case if you want to study this code, you have to download the Python 3.8 compiler and OpenSees and OpenSees 5 installation in your laptop. So I'll try if I am able to study it, but I think there will be an error for me for the OpenSeeSpy library, which I noticed a lot in my simulations. So, anyways, let's go to the discussion here. That what parameters are required. These are the definitions which are required here. The tag, we should not be worry about the tag when we are using the STKO environment. If we are using the OpenSeas, then we have to be careful about it. This is the density. For example, I have 2300 density, mass density of concrete. I'm not making it in actual value. It's just an assumption here. And for example, I have the um, elasticity up to 100 and Poisson ratio of 0.8. So, rho, it is the mass density. It's not the same density, it's the mass density. So, mass density is somewhat different from the other densities here. This is the Young modulus and Poisson ratio. And here, for the preset material, these built-in presets for the input parameter define the hardening laws here. Just in case if one point is considered here, then the STCO and OpenSeas will take care for the remaining work. If further are considered and informations are available, then you can check the tensile strength, the peak compressive strength, and the fracture energy, for which you need to have a better understanding of the curves and compressive fracture energy. Right, this is rupture strength that is given here, and similarly a tensile plasticity scale fracture of 0 and to 1, and all these compression. And then crack planes, you can define the crack plane, you can consider the scale factor for the implicit and explicit solvers, and a secant modulus if you have secant modulus, and viscosity parameter which is considered as 0 as a minimum value. Up to 0.01 we can consider these values here. So you can look at here, these are for the uh, control parameters, alpha, and all these parameters that if considered here for explicit solver can be considered. And similarly we have the crack planes. So these details are given here as well, that we should consider 44 and 45 here. So just in case if you are using the concrete, for example, I consider this value, the mass density are 2300 and 20 for the elasticity, and 518 for the concrete. And I have four planes. Let's make it one plane, and the peak compressive strength is, for example, 45 megapascal, and the unit for it is Newton and meter, and we have these values given here. Number of crack plane in the tensile behavior. So we can check them here. This is Google Peggle formulation, and it is 0. It should be less than 1. 2 by 3 or 0.67 is the default value. It is used by most of the FES softwares. So for crack planes, and it basically introduced the anisotropy in the material, and the actio crack plane is chosen based on the current principal stress direction, which is affected by the orientation of the loading and model, and the correct planes value that we are using here, NCT and NCC. This is 4 and 4 and 45. This is the by default value that we are using here, and we can change them, but let's consider the default value for internal variable. So this smoothing angle for smoothing the internal variable is something related to anisotropy, and if it is changed, the shear and flexural behavior of the concrete will drastically change in analysis. ETA, rate dependent model, eta is the relaxation time of the viscoplastic system. And if you are familiar with the Duda-Prager plasticity parameters, then you will be able to understand this, and it will be second here. So let's now test this data, right? That, for example, if you want to give it a test here, so you can see you can increase the cycle data. For example, you can convert it to 10, and you can check the material behavior. The target strain is minus 0.003, and this direction. Similarly, if you change the strain direction, you will observe that the material that we are testing here is how many effect on the parameters here. So the strain in one direction, as it is a uniaxial data, we can play with it and we can check what parameter is changing the behavior of the material that we are using here. So let's say I converted it to you can then look into these parameters here. This is for strain 11 and stress 11 direction. Let's switch to this direction, and then we should select for this the strain direction as well to check the behavior of the materials here. So then you can also switch to stress in third axis, and you can check the behavior of the material. Also, you can change the nature of the loading for cyclic testing to look into the envelope failure here, and you can make it more interesting by increasing the number of divisions according to Eurocode to see what is happening in this model. And there are some other parameters like cyclic symmetry. If you convert it to 10, for example, like this, you can look into the behavior of the material. The idea behind this whole formulation that we are using in STKO is checking the behavior of the material that we are using in our analysis. So sometime if you are not interested in uh, the behavior of the material in a detailed way, and you just want to make it crystal simple, then you can select by default values. But if you have some special purpose of simulations for activating the anisotropic behavior in a bit more detailed way, then you have to change the value of the materials here. So there are various way of modeling these parameters, and then you can get the data from this and then copy it, and you can just press on Control C and Control V, and you will get the data here. Just in case, even if you have the cyclic data, right, and here, and then you can look into the behavior of the material here as well. All these parameters are given here. So these are the attributes for the materials that you are using here, right? You can change them for the units, force units, and all these other parameters. Even you can convert it to explicit solver analysis as well. The explicit solver, it is a Baker-Boolean integration scheme, and implicit is implicit explicit is a mixed implicit explicit integration scheme, and the resulting response is um, both linear and nonlinear. So time step that is required here should be smaller, and you can then check the test data in your file using various kind of schemes here. So it's like it's not that much complex, but you can look into the nature of the loading, and you can take the data to see what is happening inside your model. And it's very sensitive in this regard, because if you change the viscosity parameters and all those steps, maybe you will get a different response that is given here. And this viscosity parameter that you are using here, that is basically adding viscosity to the material. So by using a larger value, a larger strength will be shown. By using a smaller value, a smaller strength will be shown here, as it is obvious here. If I use 0 here, based on the given data, the response in failure and roof will be different. But if I use a larger value, which is not recommended here, this response becomes something a more exaggerated way of the modeling here. So these are the and the principal axis stress strain components here. And even though if you convert to tangent formulation, you will have a different response in this scheme. And this is overall a very impractical way. If you don't know and you are not familiar with the parameters that you are using, so I will recommend you, if you are using the OpenSees and if you're not familiar with all these aspects, then you should not consider them in your analysis, and make it simple by using the one piece solver approach here. And if you have some more details, then you can explore it in analysis. For example, the way I am doing it here, so the response is changing here. And we have some sort of different parameters and material behavior is present here. So it's all depend on the availability of the data. If you have a very larger data set, then you can make it more practical by introducing a lot of complexities in it. Anyways, you can have a look at the documentation for further details and theoretical background if you are interested in it. And these details are given here. So these are some usage notes here uh, that are given here. So you can study them based on your own approach in your analysis. Thank you so much for watching.